So this is a quick summary of work, power, energies lesson. Just the theory and the derivations. What is work? Take a block, put it on a surface, apply a force like this. The body will also get displaced in the same direction. Take a block, apply a force like this. The force will get broken down into F cos theta and an F sin theta, and the displacement can happen in this direction, ds direction, and the product of force into displacement is called work done. Work is said to be done when a body gets displaced by a force. So it's F cos theta into ds, or work done is F ds cos theta. Or in other words, work done is a dot product of F and displacement vector, force and displacement vector, which will obviously result in a scalar. The SI unit is joules. Work done is joules. So then that's about this. Work is said to be done when a body gets displaced in a direction. What is positive work and what is negative work and what is zero work? When the body is displaced in the same direction as the applied force, it's called positive work. When the body is getting displaced in a direction opposite to the force, in which is the case the frictional force will be the case, where the force is always going to be opposing the motion, the work done by the frictional force here will be negative work. Work done by the frictional force. Here the work done by the applied force in displacing the body in the same direction is positive. Work done by the frictional force in displacing by a body, obviously it's in opposite direction, so it's negative. The zero work is said to be done. And let's see, when is zero work done? Coolie is going to carry a luggage on his head. He's going to put an upward force. While walking on the platform, he's going to get displaced like this. The angle between F and ds is going to be theta is equal to 90, and F ds cos 90 is a cos product, right? Cos 90 is 0. Work done will itself become 0. So then there are many other examples for negative work and zero work. Okay, let me talk about negative work. You take this spring and the block arrangement. When you apply the force here, the spring will get displaced here, and applied force was the displacement is positive force, positive work done, whereas the frictional force will be in opposite direction, and so then the displacement, the work done by the frictional force will become negative. Similarly, restoring force, there's no frictional force in this, then there is a restoring force in the spring. So in that case, the restoring force and the displacement are in the opposite direction. So therefore, the work done by the restoring force on the spring in displacing it will always be negative. And similarly, take a pendulum, the tension, which is the force, is acting towards the center, and the displacement is in this direction. Angle between F and ds is 90 degrees, so works done is said to be 0. Similarly, in circular motion also, displacement is going to happen in this direction, while the centripetal force is like this, and angle between them is 90, and so work done is 0. So then those are the cases of positive work, negative work, and zero work. So next is let's talk about a force into displacement is what is going to give you work, and it's constant force. Then the work done is calculated by finding the area here, which is F into ds. So it's work done as force into displacement is given by the area under the graph. If it's a constant force, if it's a non-uniform force like this, then you draw a small rectangle of x dx with area of this rectangle is f into dx. We integrate it from beginning x1 to final position x2. x1 to x2 is called work done, and this is for non-uniform force. This is for a uniform force or a constant force, and this is for a non-uniform force, which can be found only by means of integration. So let's go to next thing that I want to teach you in this. Thus you find the area under this graph, so you get the work done. Next is, what is kinetic energy? Okay, another thing is force. SI unit of force is Newton. Force is Newton, and 1 Newton is 10 to the power 5 dyne. And this is the CGS unit, and this is the SI unit, which you already know. So let's talk about kinetic energy. Kinetic energy is the energy possessed by body by virtue of its motion. When the body is moving, it will have kinetic energy. You know the formula, general formula is half mv square, which you already know. But how to derive this? To derive this kinetic energy, you write v square minus u square is equal to 2as, considering that the body has got initial velocity u and the final velocity v, traveling through distance s. You already know this, v square minus u square is 2as. Multiply every side with an m. Multiply every side with a half. And ma can be written as f. And this can, f into s can be written as work done. So work done therefore is kinetic energy final minus kinetic energy initial, and this is known as work energy theorem. Work energy theorem in simple terms. This is for a constant force, because you are writing m into a is f, which is nothing but a constant force. But when a variable force is applied, when force is variable, you have to do the same derivation using integration. So how do I do using it? I started as work done is equal to force into displacement. Is dW is equal to m into a into displacement, which is you can call it as dx also, displacement ds also. You can write acceleration to be m into dv by dt, velocity by time. So change in velocity by change in time into dx. And a dx by dt is velocity. Velocity is distance by time, or x by t, which is also dx by dt. So dw is m into v into dv. Now I can integrate both sides. One integration of 1 dw is just w. M into integration of v to the power 1. V is like v to the power 1. V to the power 1 plus 1 by 1 plus 1. X to the power n. Integration is x to the power n plus 1 by n plus 1. So it will become v square by 2. Where the initial velocity is u and the final velocity is v, you have to apply an upper limit and a lower limit. Upper limit is v square by 2 when you write v as v, and lower limit is when you write v as u. So it's minus lower limit, upper limit minus lower limit, which is half m v square minus half m u square, which is also k final minus k initial, which is the work done. And this is also work energy theorem. The work, how does it convert into change in energy? A delta k, which is k final minus k initial, using for a constant force and for a non-uniform force, which is using a integration method. So very important. Then from this you can, how do you derive a simple half m v square formula? Take the initial velocity as 0. If you take the initial velocity as 0, what will happen is just this will not be there. Half m u square will not be there. So this formula directly will come, half m v square is equal to work done, or kinetic energy. That's all. Take initial velocity to be 0 and final velocity to be v, and from this equation you write u as 0. You get kinetic energy to be half m v square. Simple. And same here, you get the initial velocity to be 0, then the kinetic energy is again half m v square. That's about kinetic energy equation, and how you write the work energy theorem is all based on that. Now coming to work energy theorem is over. Potential energy. Potential energy is energy possessed by a body by virtue of its height. If a body is placed on the table, it has the potential to fall down through a height h. And how do you derive it? Work done is equal to force into height h. Force itself is mg because it's falling down. Gravity is pushing it down. So work done is mgh. That's the derivation for potential energy. By virtue of its position. Energy possessed by a body by virtue of its motion is kinetic energy. By virtue of position is potential energy. So now let's talk about conservation of energy. Conservation of energy. This you have learnt it in 9th standard. You have you take a floor here, a ball here. At any instant you take this. At any instant you take this. This is our topmost point when the velocity will be 0. So this is the whole height is h, and this is x, and this will be h minus x to be these distances. Potential energy will be mgh for the whole height h, but the kinetic energy will be 0 because velocity there is 0. At this instant, if you see, the potential energy is mg h minus x plus kinetic energy will be half m v square, considering v is the velocity at any instant. And if at this position, lowermost position, it is and potential energy will be 0 and the kinetic energy will be half m velocity at the lowermost point, okay, at the lowermost point whole square. So then let's find this velocity here. To find the velocity at any instant, you should consider the top to bottom journey, because you already know the initial velocity of this journey is 0. So find the velocity, distance is yes, you root v square minus u square is equal to 2ax by 2gx. Initial velocity is 0. V square is 2gx. Substitute it here. V square is 2gx and 2 and 2 get cancelled. You get mgx. Here it's mgh minus mgx, and mgx get cancelled, and so you have answer mgh. Equation 1 also mgh. Equation 2 also mgh. Let's find the velocity for the entire journey. v1 square. v1 square minus u square is equal to 2ah. Considering the whole journey, initial velocity is 0. You can replace this as 2ah, half m v square, half m v square, which is 2 gh. Ah will be replaced as 2 gh because gravity is pulling it. 2 and 2 get cancelled. You'll still get an mgh. So then equation 3 is also mgh. So whenever you add kinetic energy plus potential energy, energy remains always conserved. So that's this derivation, and this graph is very important. The kinetic the energy versus position graph, and you can see that when a body is it's always a constant. You see, either potential energy or the kinetic energy is always a constant. Supposing this is energy versus position graph, at the topmost point you will have only potential energy. So this will be the potential energy graph. Supposing energy versus position graph, this is the topmost point. You know, kinetic energy will be 0, and so this is kinetic energy graph, and the total energy is always sum of potential energy plus kinetic energy. Okay, so then that's about that graph, and you understood it. So let's go to, that's about conservation of energy diagram. But the same conservation of energy, this diagram and this derivation is very, very important. So the second case is about take a spring, have a block at mean position x0. The object is in equilibrium. Now pull it like this. The spring will go that direction. Extreme position. Supposing consider it's moved through a distance x, not extreme position. Just say some distance x from the mean position. You know, the restoring force in the spring will act in this direction. This is not about applied force, the force that brings the spring back to its original position, and that restoring force is directly proportional to x. F is equal to minus k into x, where this k is a spring constant. Depends on whether you're using a copper or an iron, the restoring force will be different, and that's spring constant. And you know, k is equal to f by x. The magnitude of k is constant is always f by x. Okay, that's leave that alone. Now let's do the work done. dw is equal to f into dx. F is minus k into x into dx. So integrating both sides, the work done is minus k into x square by 2. And from an initial position xi to a final position xf is where this body is going. The work done will be spring constant into upper limit x final square by 2 minus lower limit is x initial square by 2. Take it inside. The work done is minus half k x final square minus half k x initial square, and minus or minus plus. So then therefore the work done is half k x initial square minus half k x final square. So initial energy, initial minus final. In this case it's getting switched like this, so it's initial minus k. Normally k final minus k initial, because of the negative sign it becomes initial minus final. This is a work done. Supposing in this supposing you want to consider that the initial position is at the mean position 0. The work done will be simply half k x square. Considering it's moving through one distance x, a negative sign can be ignored, and this is the formula for the potential work done, or it will always be equal to potential energy of a spring, which can be called half k x square. The formula for potential energy is half k x square. Very important. Okay, then when you compress the spring, it will go through this distance, this x0, and go through distance x. The restoring force will be acting in this direction. Here again f is proportional to x. F is equal to minus k into x. Work done, the negative sign indicates that f and x are always in the opposite direction. The displacement is happening like this. The restoring force is like this. That's what the negative sign indicates. But dw is equal to f into dx, again minus k into x into dx, minus k into integrating, you'll get x square by 2, which is integrated from x initial to x final again, and x final square minus x initial square will eventually become xi square minus x final square. The same derivation applies for this. You don't have to write it, one derivation is enough. So this is about, in a spring, you have to find work energy theorem, or work done gets converted into change in the kinetic energy or change in the potential energy. Here it's not kinetic energy, it's a potential energy. So let's go to next. It's about take a spring, move it, this is the supposing this is the mean position, move it to the extreme position, considering that's moved through a distance of xm, maximum distance from the mean position. Okay, you know that there will be a restoring force like this, and you have to, by conservation of, we have to find the velocity at any instant, velocity of this block at any position, for which you have to do the potential energy. What is the energy here? At the extreme position, the kinetic energy is always 0. The potential energy is half k xm square, which will be equal to, consider the block at any position, which is at a distance of x. In this case, you will have kinetic energy and potential energy. The potential energy is half k x square, and the kinetic energy is half m v square, considering it's moving with a velocity v. So can you see, we got an equation by using conservation of energy. Half can be cancelled, and k and k can be cancelled by dividing this with a k. So you get x square plus m by k v square is equal to xm square from the previous equation. Take it to the other side, m by k into v square is equal to xm square minus x square. Therefore, v square is k by m into xm square minus x square. V therefore is root of k by m into extreme position minus at any instant position. Thus, spring constant and mass of the block, you know, then it becomes easy. This is the formula. So then at the center, x will become 0. The velocity at the center will be root of k by m into xm square, which is nothing but root of k by m into xm, because xm square could come out. That's about the velocity at the center, at the mean position, because at the mean position kinetic energy will be maximum. At the extreme position, potential energy only will be maximum. That understanding you should have, and thus you can find the formula for velocity of a moving block which is connected in turn to a spring. And this formula derivation is very, very important. And in this, you know, at extreme position, this is position and this is energy. At extreme position, you know that the potential energy is only maximum. Okay, actually the graph should be like this because it's moving about the mean position, so you can draw it like this. And at extreme position, you know that it's maximum, and also you have to draw it like this. This is the position xm, which minus xm, extreme position. At extreme position, the potential energy is maximum. And at the extreme position, kinetic energy, this is kinetic energy graph, this is potential energy graph, and the total energy, if you touch here, total energy is potential energy plus kinetic energy. So this graph is also very important. This has to be like this because it's a parabola, because it involves x square. You know, x square means it's always polynomial, quadratic polynomial. Okay, so then there it was a straight line. For this first 9th standard derivation, it was only a straight line. So these two derivations are really, really important. So once you do this, you get the velocity at an instant. So that completes this. Next is about next I have to do is about collision. The collision in itself can be divided into an elastic collision and an inelastic collision. Elastic collision is one where we are considering no loss of energy. How is it possible when something is colliding? Some sound energy will be created, friction will be there. But however, we are studying like a ideal gas scenario in chemistry, like that. Inelastic means loss of energy will be there. Energy is not conserved. Here energy is conserved. That's the basic difference between elastic and inelastic collision. So I'm going to teach you something about elastic collision. Let's do elastic collision. Let's take two bodies, one of mass, bigger mass m1 traveling with a velocity u1, another mass small m2 traveling with a velocity u2. They both are colliding with each other. They're colliding, and then after which m1 has acquired velocity v1, m2 has acquired a velocity v2. So initial moment, the first equation is based on initial momentum is conserved. Momentum conservation means initial momentum is equal to final momentum. m1 into u1 plus m2 into u2 will be equal to m1 into v1 plus m2 into v2. Initial momentum is equal to final momentum. Consolidate the m1 together. This is my equation 1. m1 into u1 minus v1 is equal to m to that side into v2 minus u2. Write this as my second equation. You understood what I have done? Okay. So let's go to next. Use initial kinetic energy is equal to final kinetic energy. That is, energy is conserved. Initial kinetic energy half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. Half throughout get cancelled. You can't cancel anything else. Bring the m1 to one side. m1 into u1 square minus v1 square is equal to m2 into v2 square minus u2 square. Bring this that side. Now write this as a plus b into a minus b, u1 plus v1 into u1 minus v1, m2 into v2 minus u2 into v2 plus u2, and mark this as another equation. So what are the equations? You got 1, 2, and this is the third equation. Divide the third equation by the second equation. Compare it. This is getting cancelled when you divide. This is getting cancelled when you divide. m1 and m1 is getting cancelled. m2 and m2 is getting cancelled. So thus you get u1 plus v1 is equal to v2 plus u2. Take u2 to the other side. u1 what have we cancelled? Yeah, divide it and cancel the negatives and have only the positives. So u1 plus v1, u1 minus u2 is equal to u1 minus u2 is equal to v2 minus v1. Thus you get relative velocity before collision is equal to relative velocity after collision. Get it like this. Relative RV means relative velocity after collision. So from this you can write a formula for, take the v2 to the other side and write u1 minus u2 plus v1 is equal to v2. Take this and substitute in the first equation. In a conservation of momentum, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2 you write it u1 minus u2 plus v1. Now take it in and multiply. m1 v1 plus m2 u1 minus m2 u2 plus m2 v1. You can take this to the other side and make it 2m2 u2. Okay, you want to find v1, that's your objective. Consolidate the v1. v1 into m1 plus m2. Take everything to the other side, you get m1 u1 plus 2m2 m2 u2 minus m2 u1. So you can bring this down. Thus you got the velocity v1. For the velocity v1, I'll just tell you a simple example. If you know u1 and u2, you can multiply m1 minus m2 by m1 plus m2 plus 2m2 into m1 plus m2, and you can memorize this formula. That's what you eventually will get. That's the velocity of the first body. Because we substitute v2 in terms of v1, obviously we can get v1. If they ask you v2, don't worry, just change it around. Write u2 into m2 minus m1 by m2 plus m1 plus 2m1 u1 by m2 plus m1. Just change the alphabets, that's all. So then thus this is a very crucial formula, which is velocity v1. If you know u1 and u2, you can write m1 minus m2 by m1 plus m2 plus 2 into m2 by m1 plus m2 here to memorize it, and thus you get this formula in which there is a case study. What happens when m1 is equal to m2? This will get cancelled. Correct? When the masses are the same, 2m2u2 by, this is mass is same 2m and this is also m. So you get u2 is equal to v1, which means the velocity is getting exchanged. The second body's initial velocity is the first body's final velocity, and vice versa. That's all. So that's the first case. That's a case study number 1. Case study number 2. Supposing there is a huge second body which is not even moving, and there's a small first body which is moving with the velocity u1. It comes and collides. You know, obviously, common sense. Since m1 is much lesser than m2, it comes with the same velocity and goes back with the same velocity. So final velocity can be written as minus u because the direction has changed. But you have to get it using this derivation. What is the derivation? You know, v1 is equal to, what do you write? A u1 here, a u2 here, with multiplied by m1 minus m2 by m1 plus m2, and plus 2m2 u2 by m1 plus m2. In this, if the masses are the mass is bigger, okay, but it's static. I think the masses are the one body's mass velocity u2 0. u2 0, this becomes 0. u2 0, that becomes 0. So I'll get v1 to be of this formula. But what happens when both the masses are the same? Then v1 itself is becoming 0 because m1 minus m2 will become 0. But you are supposed to get a minus u. So if the m2 is much larger than, okay, I'll just redo it. If m2 is much larger than m1, you can ignore m1, ignore m1, ignore m1, ignore m1. So it's going to become minus m2 and m2 gets cancelled, minus u1. You know, the second velocity is anyway 0 is equal to v1. So v1 is equal to minus u1, and we got what we want. So that's the second derivation where m1 is much lesser than m2. I missed that. The third one, I think that's it. So any such case comes, you can substitute it in this equation, and this equation is the crux, and you have to substitute it there and observe what's happening. So let's go to next derivation, which is about inelastic collision. In an inelastic collision, what happens is, let's take m2, which is not moving. Let's take m1, which is moving with the velocity u1. In inelastic, there is loss of energy. Remember, there is loss of energy. There will be delta k. K final minus K initial. Here in this case, K initial minus K final. Because the body is already moving, over some time it loses energy and final will become less after colliding. So then it's here you can use conservation of momentum. And you should understand that both the bodies are going to move as one unit with a velocity v. So initial momentum is m1 u1. Is going to be equal to final momentum, which is m1 plus m2 into v, from which you know v is equal to m1 u1 by m1 plus m2. You got the formula for velocity. You can't use conservation of energy. You can only use delta k, which is k initial minus k final. K initial is half m1 u1 square, because only one body, smaller body is moving, the bigger body is static. Minus k final is half of m1 plus m2, because both the body are moving together with the velocity v square. But instead of v square, I can substitute this v, and so it will become m1 square u1 square by m1 plus m2 the whole square, where the whole square get cancelled. You can take half and an m1 outside. So you will, and a u1 square also outside. You will get 1 minus m1 by m1 plus m2. You take an LCM, half into m1 into u1 square. LCM is m1 plus m2 minus m1. m1 get cancelled by m1 plus m2. I would like you all to memorize the change in energy is half m1 m2 by m1 plus m2 into u1 square. Only the smaller body has velocity. No, this is what is a k final. Now they ask you ratio between k final and k initial. Now this is the loss of delta k, change in energy, not k final. They ask you ratio between k final and k initial. K final is half into m1 plus m2 into v square. You know, v square is m1 square u1 square by m1 plus m2 the whole square, where this and the power get cancelled. And the k final is half into K initial is half into m1 into u1 square, only the smaller body, so half and half get cancelled. m1 and m1 power is getting cancelled. u1 square and u1 square get cancelled. You simply get m1 plus m1 by m1 plus m2 is ratio of K final by K initial. Since the denominator is always greater than the numerator, you know K final is always lesser than K initial in the cases that we have studied. Because we are already considering it to be a moving body which loses its energy and slows down. Okay, so then next about coefficient of restitution. Coefficient of resilience, or in other words restitution. What is this? Is given by E. E is equal to V1 minus V2 by U1 minus U2. U1 minus U2 with a negative sign. Just relative velocity final minus relative velocity final, initial. So don't worry about this. I'll just straight away mug this up when E is equal to 1, which shows that perfectly elastic collision. When E is lying between 0 and 1, we can say it is inelastic collision. When E is equal to 0, you can say that this refers to the bigger mass which is not moving, and a smaller mass which is moving with the velocity comes and collide. They move as one unit, no, stick to each other more. That is when you because there's no V1 and V2, it has got only one velocity, and so E will be 0. That's this case. And E will be greater than 1 in a case where Sanjana was referring. Like what happens, the initial velocity is 0 and the energy is going on increasing. In that case, that's this case where E will be greater than 1. Just get to know this, and that's about it. There's one more derivation in this which I'll do it next class.